Hi everyone, this is the update for Science and Force Fields at OpenFF for February. And fun fact, we're actually in the middle of our in-person work week at UC Irvine in California, so I'm actually recording this update from the United States. Um, so getting right into it, since joining Jen has been hard at work on QM datasets and a collaboration with Genentech and the Cadera Lab to create a transition metal force field. So for this first project, she's moved on to parsing data from published databases, and we're still in the process of seeing if we can get access to new data. So we're talking to the CCDC in the UK to see if we can access data from the Cambridge Structural Database. In terms of actual data sets that are computing, both of the data sets submitted by ICARA are now complete. The lipid datasets, both the optimization and benchmarking datasets, are still ongoing. And we've actually received a new submission of additional molecules from Crescit, from Matthew at Crescit, where he identified 5 cases where our torsions seem to fail to reproduce the correct QM profile, and has put effort into identifying around 70 additional molecules that should help improve data coverage for both diagnosing and fixing those cases. So that's computing away now. And lastly, Jennifer has been working on dataset strategy, and she'll be gathering input from stakeholders more during this in-person meeting, where she's been investigating formats for sustainable dataset archival beyond Open Force Field's current software stack. To update on one of our other major roadmap items for this year and for the past couple of years, this is the creation of a new force field that contains self-consistent parameters for both proteins and small molecules, driven by Chapin Kamada in the Gilson lab. So Chapin has been looking at an approach where he reweights torsion parameters to NMR observables, and he's, in terms of progress since last month, he has continued validating his workflow on a toy system of butane and fixing some bugs identified along the way. In the meantime, he's continued iterating on the proper NMR GB3 workflow, although we do still see that there remains high variability in free energy profiles between the GB3 native contacts between different replicates, suggesting poor sampling. So to address this issue, Chapin is planning to firstly simulate additional replicas, as well as looking into replica exchange while those are computing. With the additional iterations on the NMR workflow, he finds that iterating more makes the native basin more favorable in the free energy profile, but also generates secondary minima along the way. So Chapin has also been working on a cumulative fit workflow that pulls samples from multiple runs, under the hypothesis that that should improve performance. So in progress is still further code validation, as well as continuing to work on NMR fitting. On the open force field side, as mentioned last month, we started looking into some parallel approaches into the QM data fits. So essentially, trying to ask questions as to why fitting to QM data seemed to work for amber force fields, but weren't working for the Smirnov force fields. And we were looking at a couple of different research questions, and these investigations were started by Brent and Lexi before they left. Where the first one was wondering if whether our existing fits were getting stuck in a local minimum, essentially, and whether loosening torsion price might help them get out of that minimum. So Brent ran this fit before he left, starting from stage 2.1 and following Chapin's workflow. And what we largely see is, compared to previous fits that Chapin ran within our force field, as well as our published Sage 2.1 force field, this workflow seems to largely give us somewhat weaker torsions when we look at torsions relative to proteins and specifically the protein backbone. Last time I mentioned that we were looking into some explosions in the GB3 benchmarks. We identified that the explosion with this particular model was basically an error where we forgot to add constraints. So adding those allowed us to actually simulate GB3 without the simulation crashing. Although unfortunately, we did see that the secondary structure of the helix that we see unravel in other simulations is also unraveling here. The second approach that we were looking at is whether we might be overweighting the representation of small molecules in our training data set. And if we only fit to protein data, wondering if that might give us somewhat more similar performance to the amber line of force fields, which also primarily fit to protein data. So for this question, we fit a number of models, which I've highlighted here. A couple descending from the Smirnov heritage, with both the null model and the specific model, and a couple descending from AMBER 14SB. And we fit two different force fields with AMBER. We fit one with default weights, so where each training target was essentially given the default weight in the training data set, and one that we called equal weights, where the protein torsion drives were upweighted, had their contribution to the objective function scaled up, such that the sum of the protein torsions numerically matched the scale of the sum of the optimized geometry function targets. So this was pretty interesting because we saw that when optimized geometries contributed most to the objective function, we got a force field where simulating GB3 both resulted in a stable simulation and one where the secondary structure didn't change, remained stable throughout the simulation. But however, once we upweighted the protein torsion drives, not only did basically we didn't see GB3 actually unravel, but we did see the protein simulation explode. With the Smirnov force field fits, one of these fits, the specific model, did result in a stable GB3 simulation, although the helix still unravels in the benchmark. But we actually also had another force field where the simulation explodes. And when I say explodes, I mean we get NAND errors at some point into simulation. So why was this happening? Over the past month, we spent some time debugging, and we think this might be because some of the valence terms are getting much weaker after the force field fit to the point where they're approaching zero. So in one replicate of the Smirnov null model fit, where we simulated GB3, we were able to isolate an instance of the crash. So this tyrosine residue had the aromatic ring distort quite severely before finally imploding. And we think that might be happening because some specific valence angles, so specifically this aromatic hydrogen, is becoming much weaker, as shown here, where the green line, the exploding force field, is much weaker than previous similar force field fits. It was much more difficult to isolate the crash in amber because these crashes tended to happen either hundreds of nanoseconds or even microseconds into the benchmark. But we did see similar angles where it either became much weaker or in one case actually inverted. And these were actually even more relevant to the protein. These were protein backbone angles. So we think this might be why the amber equal weight refit is also exploding. So as I mentioned, one of the Smirnov fits didn't explode, but we did see the helix unravel. So that's a specific model protein only fit. And unfortunately, we see the protein essentially fall apart in at least one replicate. And finally, the last project that I'd like to give an update on is an update to our fitting protocols in Evaluator. So as mentioned last time, last year, the Schertz group identified several issues with Evaluator fits. And we used Evaluator to fit van der Waals parameters to condensed phase properties. And there were several issues here where the temperature wasn't being held to the desired state and there was spikes in the energy, both of which have now been resolved. The last issue, where insufficient sampling was leading to wildly varying estimates and properties, we spent some time looking into and came up with a new workflow where we first pre-equilibrate a box and then compute properties from that equilibrated box, as well as adding in measures to increase sampling, which now provides much closer estimates. So that's progressing. But another finding that we wanted to give an update on was that the particular property that we initially noticed this for and were used to debug, we realized was actually very, very difficult to converge and to equilibrate. And the hypothesis here is that that might just be a very viscous component or molecule. and just be difficult to work with in general. So we had a look at the viscosity of the training data sets or the properties in the training data set that we were using. And looking at the experimental viscosities that we were able to find from SOMA-ML, we saw that only a small fraction of the training data set included components as viscous as this particular property, which was triethanolamine, and is highlighted with the arrow here. Given that we spent a significant amount of effort now trying to get triethanolamine to behave without a lot of success, we propose instead to move forward by filtering out future training data sets to just not include these difficult components and using either experimental data from SOMA-ML or even computing our own viscosity properties to create this future blacklist or whitelist. So that's it for what's been going on with science and force fields this past month. I'm sure we'll have a lot to update on after this in-person work week. So see you next month. Thank you.